In this lab, you will observe the establishment of an LDP pairing between routers 1 and 2. Begin by checking the status of the MPLS interfaces with the command show MPLS interfaces. No interfaces are currently displayed in the output because no interfaces are MPLS enabled. On router 1 and router 2, enable MPLS on interface gig00 with the command MPLS IP. When MPLS is enabled on an interface, so is the label distribution protocol. It is used to exchange label binding information after an LDP pairing has been established. Issue the command show MPLS LDP neighbor to view the status of the pairing between router 1 and router 2. There is no LDP pairing. Let's take a look at a packet capture. To discover an LDP neighbor, routers send LDP hello messages. Hellos are sent on UDP port 646 to the all routers multicast IP of 224.0.0.2. We can see that the hellos are being sent, but no pairing is forming. Take note of the source IP of the hello messages. We can check the information related to the locally generated hellos and neighbor discovery with the command show MPLS LDP discovery detail. The output reveals that the hellos are being received. Here's the issue. There is no route to the transport IP. How strange, considering the source IP of the hellos was that of the connected network. Let me explain. When MPLS is enabled, a router ID is selected. Like many other protocols, the order is a manually set ID, followed by the highest IP of a loopback, then the highest IP on an active interface. Part of establishing an LDP pairing is establishing a TCP connection on port 646. This connection is established using the transport IP, which is reported in hellos. However, it is not always the same as the source IP. By default, the transport IP becomes whatever value the router ID is set to. In this case, the router IDs are set to the respective loopback 0 interfaces on router 1 and router 2. The problem is that neither router has a route to the other's transport IP, thus preventing a TCP connection from forming. This could easily be resolved by creating static routes or by advertising the loopback IPs into an IGP. I am going to use alternative methods because I want you to get a better feel for the relationship between these different IPs. On router 1, issue the command MPLS router ID gig00 force. This is a good command to remember. Now check the discovery information on both routers. On router 1, see that the router ID and transport IP are now the same as the source IP, derived from interface gig00. The previous command changed the router ID, which resulted in the transport IP changing too. The force parameter is needed because a router ID has already been selected, and I want the change to take effect immediately. Router 2 no longer shows no route to transport address. Instead, it now shows no host route to transport address. What it is saying is that there is no /32 route to the transport IP of router 1, but that is not required for the pairing to be established. Router 2 now shows router 1 as reachable on the connected network. Under router 2's gig00 interface, issue the command MPLS LDP discovery transport address interface. Whew. Router 2's discovery output shows that the transport IP now reflects what is assigned to interface gig00. However, the router ID remains unchanged. Issuing the show MPLS LDP neighbor command reveals the pairing is established. This line confirms this. So remember, the IP sourcing the hello, the LDP router ID, and their transport IP serve different purposes. They can be the same value, but they don't have to be. In the next lab, we'll observe the basics of LDP label binding.